Thanks for joining the very first AI4OPT seminar in spring 2023. So, as you all know, we have a exciting line of speakers for the semester. The schedule is all on the website, and all the seminars will be in this room with great lunch. So today we have Professor Anirbit Mukherjee from University of Manchester. So I have known Anirbit since our undergrad days, and Anirbit's research interests are broadly in training algorithms and generalization guarantees for neural networks. I like to call Anirbit deep learning theory evangelist because, and you'll see why. So Anirbit got his undergrad from Chennai Mathematical Institute in physics, and his master's also in physics from Tata Institute of Fundamental Research. He got his PhD in applied math from Johns Hopkins University. And as I mentioned, he's currently at University of Manchester. He also did a postdoc at Wharton. He's recognized by several awards, Minds Data Science Fellowship and Walter Robb Fellowship during his PhD. And more recently, he has been selected as a member of ELIS Society, European Laboratory for Learning and Intelligent Systems. So today he's going to talk about his work on theory of two-layer neural networks without further delay. Anirbit, the floor is yours.
Thanks, Shiva, for the amazing introduction. Thanks to AI4OPT for the invitation and for the amazing arrangements. I hope the talk is worth it. So let me get started into it right away. Okay, step one. Does this work? Okay. Is something okay? Great. Okay, I don't know how many of the audience are already familiar with neural networks. Just to give a quick overview of what neural nets look like, here is a good example to keep in mind. What you see on the screen is a simple neural net with two inputs in the green vertices, leading to one output at the red vertex. It has 4 activation gates with the blue vertices. The topmost blue vertex is getting 2 wires as input with weights 1 and -1. Sorry, with 1 and 1. The second one gets 2 wires with weights -1 and -1. And similarly for the other gates. So the output of the first gate will be max of 0, x1 plus x2. Output of the second gate will be max of 0, minus x1 minus x2. Then you can create a weighted sum of the outputs of the 4 gates, with the weights being half minus half, half and half, and convince yourself that this network is computing the max of 2 numbers, which is coming as input. So here's a very simple example to keep in mind of how max of 2 numbers can be computed by a depth 2 width 4 neural network. It's a very nice example to keep in mind if you have never seen neural nets before. Of course, max functions are very useful for building neural network theory, and at some point we used to do a lot of this, but we have moved on for other things. To define more formally, the ReLU activation is what is most often used. It is a map from Rn to R. You should think of it as a map from Rn to R, which takes a vector and gives max of 0, the corresponding coordinate as output. A neural network of depth k plus 1 will be consisting of k plus 1 alternative compositions of an affine transform with activation. So the input comes in at the A1 end. It passes through A1, then goes through ReLU, then goes through A2, then goes through ReLU, and does this k plus 1 times. So my convention will be the depth of the neural network is the number of affine transforms, which matches the convention in graph theory of the graph distance from input to output. If you think of it as a graph, then this notion of distance matches the graph distance notion. That's why I like this convention of number of affine transforms is depth. Okay. Also, so a little bit more terminology. When we have just an architecture like this without any weight assignment, we should think of an architecture as specifying a full neural function space, because you can assign any weights to the edges of this graph and you get a different neural function. So we want to make a distinction between an architecture and a neural function. So an architecture is a function space, whereas a neural function is an architecture with a weight assignment, just to make clear the terminology. Why are such functions exciting? Because of experiments like this. These are outputs of a neural network. It's a very famous experiment you can Google up. You can go to the website called thispersondoesnotexist.com. Every time you refresh the website, you get a new human face as an output of a neural network. So it's a very famous experiment. These kind of experiments is what got people like me excited. What the heck is going on? Why are these functions producing human faces as outputs? Okay, but this is only the one tip of the iceberg of the reasons why neural nets are exciting. Currently, there are many other reasons to be excited about, but that's separate. Of course, the problem with neural network theory is that it's an optimization landscape. Ultimately, it's an optimization problem with a landscape which is extremely complicated. What you see on the screen is an actual photograph of a two-dimensional projection of a neural landscape. And this is from a very famous paper called Visualizing the Loss Landscape of Neural Nets. So they interestingly pointed out that the left diagram and the right diagram are the loss functions of a neural network, which differ very little in their architecture. So you can make very small changes in the architecture and cause a dramatic shift in what the landscape of optimization looks like. It's kind of believable if I say that the left one is harder to optimize over than the right one. But how do you know you are in which picture? Because left and the right pictures differ very little in architecture, actually. I think if I remember correctly in that paper, it was just one gate. They had to change one gate slightly and this picture changed from right to left. So there's tremendous sensitivity to the shape of the landscape to how the architecture looks like. And that's what makes this thing so very complicated to handle. And even when things are complicated, we somehow, the overwhelming experimental evidence is that there is very little need of algorithmic ingenuity. So creating specialized algorithms is not a thing in deep learning in some sense. There's basically one or two good algorithms which will work in 99% of the neural nets you ever see in your life. And that's kind of the mystery. Why do simple algorithms work so well universally across so much of variation in architectures? Yes, question?
Yeah. All right, just a clarification. What do you mean by skip connection?
Okay, the skip connections basically is when you have a node which takes the input to the output directly without passing through the architecture. Those are called skip connections. So that's how this paper had this way of changing a skip connection to change the picture. The real point, thanks for the question. The real point here is that why are simple algorithms so dramatically successful? Like you don't have to invent new algorithms every time a new neural net comes up. And that's the real challenge of deep learning. There's essentially one algorithm which works for everything you ever see, more or less. That's a fair statement to make. Okay, so let's see what is known about Provably about neural net training. So when I started the research, one of my first results was this in 2016, where I had shown, we and my collaborators had shown that if you take the single layer of hidden gates neural network with ReLU activation and consider the loss function, which is given here, which is the empirical minimization problem, empirical risk minimization problem over arbitrary data xi and yi, when the data is being passed through a one layer of ReLU gates. This is a non-convex empirical risk minimization problem, and we were able to show that is exactly doable for every data, every width, in a runtime which is exponential in width, polynomial in the training data size, and also exponential in the input dimension. The exponentiality in the input dimension is unavoidable because that comes from certain NP hardness results. There's results from Georgia Tech about this actually, about this NP hardness results. The exponentiality in width is very interesting. We could not remove it, and I will slowly make some comments about it. But the interesting thing was this was polynomial in the training data size. So before this result of ours in 2016, it was not known if there is at all a fundamental barrier to getting poly training data size global minima finding on neural networks or not. So we were able to establish that there is no complexity barrier in that sense. In recent times, I think this result has been slightly improved. Where did I go? So in recent times, this runtime has slightly improved now. Since 2016, many people have, for surprising reasons, I might say, a lot of people got excited about this result. And this has led to many follow-up works. So now, last I know, there has been an improvement to this runtime. It is slightly lower powers have come up, but still exponentialities have not really changed. And I think most recently, there was a paper from UT Austin by Adam Clavance's group who have shown that up to some complexity conjecture, this 2016 result is near optimal. There has been a reduction now shown, I think. So this is almost unimprovable now, we know after 6 years of research. Okay, so this is about exact training, that exact training is possible. Of course, such kind of questions are still open for high depth nets. High depth nets, can you find the exact global minima by some algorithm given any amount of time? That's not clear. Okay. So it's fair to say that the proof of trainability remains open in almost anything useful. Any useful neural network architecture data, the proof of trainability is not clear. So in 2020, we embarked on this plan of, let's say, what is the smallest non-trivial problem we can frame here? One of the smallest non-trivial problems we can frame is to say, let's say I want to train a single ReLU gate. I want to use non-realizable data, and I want the algorithm to resemble SGD. SGD is most successful, non-realizable data is most natural, and the simplest neural net to have is a single ReLU gate. So at this trifecta, can you write a proof? That was the challenge we tried solving in 2020. And we have some interesting results with that. So this would be the question.
The previous result is not for SGD.
Which one?
The empirical risk minimization.
Yes. This is the exact global minima finding algorithm.
Is that SGD?
No. The idea was basically to splice up the problem into a sequence of linear programs. The whole idea was that we could, it's a combinatorial optimization problem over linear programs, and we could get a runtime out of it.
And clarification, what is N? N.
Yeah, N is the input dimension.
Okay.
So that's the NP hardness, basically. Okay. So simplest setting for a single ReLU gate training would be an algorithm like this. So you take up an arbitrarily chosen starting point for the algorithm W1. It's an iterative algorithm. We sample a batch of B samples from the data, from the distribution D. We query an oracle with your sample data. The oracle returns back the evaluation of a single ReLU gate at your sample data, but adds to it a distortion, which is probabilistic and bounded. So alpha TIs are biased coin tosses, and xi TIs are a distortion, which is bounded distortion that's adding. So this is like a data poisoning attack. It's the simplest model of a data poisoning attack on a ReLU gate. And then I'm constructing out of the sample data. So then I'm constructing out of the sample data this proxy gradient. If you stare at it carefully, this looks almost like taking the subgradient of a squared loss on a ReLU gate. The first two terms should be resembling to that. But the indicator, you notice, is on the labels. So I'm measuring whether the label is greater than the maximum distortion allowed or not. And this small little change from the stochastic gradient descent or stochastic subgradient is what makes the whole thing work. If we come up with this small distortion to the true subgradient of this loss function, then it turns out this algorithm is provably convergent to the global minima in the no distortion case. And the with distortion case, we can give guarantees on how close it can get to the original global minima in how much time. So the non-asymptotic guarantees are possible about approximate convergence when you have the distortion. And there are many cool features about this particular algo result, which I can get to. For example, you can do a side-by-side comparison of actual stochastic gradient descent on the right-hand side and our modified stochastic gradient descent on the left-hand side. So in this particular diagram, the probability of attack on the labels is kept constant, and I'm varying the magnitude of the attack. So clearly the blue line is when no attack is happening. So its true labels are being received by the algorithm. And then I'm slowly increasing the attack from blue to the red. Similarly on the both sides. And you can see that the modification I did to the subgradient essentially seems to have no influence at this level between the trajectories of the algorithm. The true stochastic gradient descent and my modified stochastic gradient descent seem to have nearly identical behavior at the squared norm dynamics. While the right-hand side picture is still not proven, but for the left-hand side, we can give a proof. So in terms of, one might say that in terms of stochastic processes, we realized experimentally that these stochastic processes are probably very close to each other. But one of them is provable and the other is not, while they differ in the specification just by a very small term. And that's enough to make the theory be possible or not. And I should point out that this is a linear time convergence in the no distortion case. So this graph, I would say, should motivate you to believe that in the no distortion case also, stochastic gradient descent has a linear time convergence, which, as far as I know, has not been proven in distributional generality. It's only for certain specific distributions is this proven. So this plot, even in the no distortion case, to the best of my knowledge, is not yet fully theoretically explained. If you have distortions, then essentially I know of no guarantees on SGD at this point. But with our distortion, with our slight modification, you can get guarantees. And this kind of a picture remains essentially invariant if you look at it from the other point of view, where now I'm essentially fixing the probability of attack, but varying the magnitude of attack. Even then, it's essentially the same picture. Blue is the no attack. You can see at no matter what the value of the attack is, the behavior of SGD and our modification is nearly looking the same. While, as always, the right-hand side picture, we don't have a proof. I don't think anyone has a proof to the best of my knowledge, but left-hand side, we can make a proof. So provable convergence is possible if you slightly change the SGD. And this is, I think, an interesting mathematical observation. This was essentially the first linear time convergence on a ReLU gate, while neither fixing the functional form of the data nor making symmetry assumptions about it. So we do not assume that the distribution of the data is symmetric. We do not make assumptions about the functional form of the PDF, but we can still get linear time convergence. And I don't think there was a previous result to that. Additionally, in this case, as I pointed out, that we can give approximate convergence guarantees when there is a distortion, which is still open for SGD. I don't think there is a SGD result yet. Question?
What do you mean by convergence? So convergence to your local optimal or
global optima, because it's a realizable model. So because it's a realizable model, in the no distortion case, there is a W star true weight which is generating the labels. So the algorithm converges to the global optima of W star.
So is this depends on starting points?
No, it's arbitrary starting point.
Are you unique optimal?
Yes, it's an unique optimal solution. Essentially, the proof of the convergence of the algorithm can be sort of thought of as a uniqueness argument also. There is a unique optimal here. Okay.
Is the objective convex?
Nope, it's not convex.
Okay, but still you get global convergence and you get linear convergence.
Yes.
And no noise here, right?
Even no noise is linear time. If you had noise, things are a bit different. Cool. So far, this is about single gates. So the question of provable training, of course, I should point out that there is, let me just go back this. So I should just point out that there is a partial multi-gate extension of this result currently on arXiv. It's a paper with the same co-author Shire Kormukar and Theodore Papamarkiou. If you go on arXiv, you'll find a paper with me, Shire, and Theodore, where we have a partial multi-gate version of this also. But it's partial for reasons you can understand. When you read the paper, it will basically, we have to assume a convolutional structure in the net. If you assume a convolutional structure in the net, then we can get a certain amount of multi-gate version of this result also. But it's not fully multi-gate because there is a convolution structure. Okay, so let's take a step back to see, with gradient-based algorithms, what do we really know? So stochastic gradient descent and its variants, like Adam, RMS prop, AdaGrad, AdaBoost, I don't know how many of them have come up currently. They're all wildly successful and surprisingly easy to write algorithms, but they're wildly successful across a huge variation of neural nets architecture and data. And this has essentially never been explained. Why is such a simple algorithm like SGD so well working? In this, the rest of the talk, I shall try to establish, probably for the first time, that SGD can converge to the global minima of certain loss functions while making no assumption on the width and the data. So that shall be the second half of the talk, essentially. But to get to that result, I want to first give a historical overview of where things stand. One of the most prominent approaches to gradient-based training of neural networks is what is called the neural tangent kernel, the NTK approach. The idea in the NTK approach is essentially to say that if you want epsilon target accuracy, then start with a neural net whose width is poly 1 over epsilon. You can actually get it to polylog 1 over epsilon in one case that was studied by G and Telgarsky. And in that limit of width being poly 1 over epsilon, the predictor becomes effectively linear in the weights. And then the mathematics kicks in to get your global convergence. It should be pretty obvious, I believe, that this is a clearly unrealistic regime. This kind of large nets don't exist in the real world. Such weirdly wide nets is not a realistic assumption. In fact that it's not a realistic assumption can be studied in a very interesting point of view, which you say that when the training happens, you sample one image and you make a SGD update based on that image, and you can ask how much does the prediction change at other images. You sample a cat image. By sampling a cat image, how much does the prediction change at a dog image? It's a valid question to ask. And you can look at this microscopic structure of the stochastic gradient descent during neural training. And that is called the study of local elasticity. From the local elasticity point of view, in fact, it becomes very visually obvious that the limit point and real nets behave differently. In some sense, this change of one data point on the other, the effect of sampling one data point on the prediction at other data point, this 2-point behavior is extremely different at the limit point versus real nets. And this kind of becomes apparent from there are many ways to make it apparent. One of the ways is, I would say, is local elasticity viewpoint. So I would encourage the readers to go and read this paper of ours, where we have done an extensive study of this local elasticity phenomena of deep learning. And that as a result along the way shows why the NTK limit point and real nets are very different things. Another approach to provable multigate training has been what is called the mean field approach. In the mean field approach, we essentially replace the study of neural weight dynamics in finite dimensions by a study of flow of probability distributions, the space of probability distributions. So you're in some sense shifting a finite dimensional non-convex optimization problem into an infinite dimensional convex optimization problem. So you pay the cost of convex, you get out of non-convexity by paying the cost of going to infinite dimensions, and then you can get convergence in the distributional space. But it's pretty clear when you look at the proofs that this makes sense only when you have really infinite gates. It's not a real world neural network. I don't know of any way of going back to real world neural nets result from a mean field convergence result, because this is always sitting at infinity. Okay, so here's a brief summary of the history of the field of provable convergence. To the best of my knowledge, probably the first significant multigate convergence was 2015 by Janzamin et al. In 2015. It was recently improved by Awasthi et al. In 2021. Then in 2016, we gave the first deterministic any width, any data exact convergence that I started the talk with. 2017, Zhong et al. Gave a proof of gradient descent on depth 2 nets with realizable data and Gaussian distributions. This was hugely improved in complexity of the runtimes, etc., by Zhang et al. In 2019. 2018, when the lazy differentiable programming approach came to view by Chizat and Bach, this led to the first NTK results by Jacquot et al. In 2018. 2019 is where I know the first multi-depth NTK result showed up. This was Alan Zhu et al. Then in 2021, there was the first mean field for deep resonance proof showed up by Fang et al. 2021. So this is a very personal, selective, incomplete, and highly biased survey of neural net theory of provable neural training in the last 7 years. So some highlights of what has happened in 7 years. In summary of all these papers, I would say is that what has remained an unresolved challenge is whether you can get SGD to converge on any neural architecture with constant number of gates while neither constraining the labels nor the marginal distribution of the data to a specific form. If I want to remove the assumption on the number of gates and the assumption on the data simultaneously, can I still get SGD to converge? This is a central unresolved problem in the field, and let's see if we can make some progress about it. So our story begins in this paper, arXiv 2004-06977 by Bin Shi, Weiji Su, and Michael Jordan. In this Shi et al. Paper in 2020, they had studied SGD by, like many others have also done, studied SGD by studying the continuous time limit of a stochastic differential equation. And they had studied this particular form of the SGD, which is the very standard form of step length S. You're sampling a mini batch, computing the gradients of the mini batch points, and changing the gradient by it. And they had said, and they had pointed out that you can write down a SDE which was provably close to the SGD that you saw in the last slide. And by using the standard machinery of SDEs, one can show that if WS is a random variable following this SDE, then the density of the random variable follows the Fokker-Planck Somolotchowski PDE, which is given by this. It's a pretty complicated PDE, but actually good, not too hard to solve either. So this was their approach. And once you convert this to this FPS PDE, you can start making an interesting observation. The key observation they made was that if your loss function L tilde is what is called a Villani function, then the FPS converges to a Gibbs measure of the loss function. And there's many subtleties in this argument actually. This convergence is asymptotic if you do not assume all the parts of what it means to be a Villani function, but the convergence is non-asymptotic with a known convergence rate if you assume it to be a fully a Villani function. So that's the difference between what's called a confining function and a Villani function. That this PDE has a stationary distribution. The stationary distribution happens to be the Gibbs measure, and this Gibbs measure you can actually compute how fast the convergence happens to this Gibbs measure, and your ability to compute the rate of convergence to the Gibbs measure is essentially comes from the assumption of the Villani structure. So I really would like to emphasize the distinction here. Maybe it's a very technical point, but I like to emphasize this, that convergence to the Gibbs measure does not depend on the assumption of Villani-ness. It's the rate computation which really depends on the Villani-ness. And probably to the best of my knowledge, this idea of a Villani function first appeared in Cedric Villani's 2009 monograph called Hypercoercivity. This is probably the first place where this was pointed out. And these guys figured out how to use it right in the SGD context. So what is a Villani function? So a function is said to be Villani if it satisfies these 4 conditions. First is it's C infinity. Second is it blows up to infinity asymptotically. Third point is it has density in some sense. E to the power of -2 by f is integrable for every weight s. And the fourth property is what is, I would say, is the most critical and the most difficult or the most non-intuitive property. It somehow tries to balance the square of the norm of the gradient with respect to the Laplacian of the function. In some sense, asymptotically, the square of the gradient norm has to grow faster than the Laplacian. And this is a very critical condition, which is what makes the whole thing the whole trick comes from there. If any function satisfies the first 3 bullet points, it is called confining. If it satisfies all the 4 conditions, it's called Villani. So their key idea was to say that if you have a Villani function f, then you can define a Gibbs density for it and show that the Gibbs density satisfies a Poincare type inequality. So the variance of any compactly supported infinitely differentiable function is upper bounded by s by 2 lambda s into expectation of the square of the norm of the gradient. So this is sort of like the proof where the Villani function, the 4th condition of the Villani condition gets really needed. I don't know how to prove this kind of a Poincare inequality for the Gibbs measure unless you assume that your loss function is Villani. And the need for the Poincare type inequality comes when you want to know the rate of convergence of the FPS PD to the stationary measure. Okay. Please stop me if you have any questions in case we have enough time, so we can go slow. Any questions? Okay. So in their paper on page 9, they had made an interesting comment that some loss functions used for training neural networks might not satisfy this condition. And this got me curious when I read the paper the first time. So how hard can it be for this mechanism of proving SGD convergence to work for neural networks? Where is really the blockade coming from? So I pursued this idea, and let's set up our problem very clearly. So I want to look at depth 2 neural networks, 2 layers, mapping from Rn to R, where I'm freezing the second layer to a vector A transpose, and the first layer I have a matrix W, and the activation function is sigma, which I shall specify. And I'm going to choose to work in this particular loss function, which is squared loss plus a Frobenius norm regularizer, which is a very standard loss function used in the real world. And we shall assume the activation is kind of nice in a certain way, is that it is bounded, it is C infinity, it is Lipschitz smooth. And there are first and the second derivatives of sigma are also bounded. And it's easy to see that pretty standard activation functions satisfy the conditions for this, which is tan h and sigma t. We can relax the boundedness assumption, but then we cannot get discrete time convergence. So that was already pointed out in the, it was not pointed out exactly in the original paper of Beiji, Su, and Pinshi and Jordan, but it's kind of, if you think through it, it happens. Okay. So then we get to the main theorem. What we have in the main theorem is that for the activations that I considered, which was bounded, Lipschitz smooth, and everything, the loss function turns out to be gradient Lipschitz. And then I can say that there exists a constant, a critical threshold of regularization lambda c, such that for all lambda greater than lambda c, the loss functions will satisfy the Villani condition. This is the key point. Once I can get a neural loss function which satisfies Villani conditions, I can straight up start to get a SDD convergence out of it. The machinery kicks in. Essentially, the machinery was always ready. It is all about noticing that you can get neural losses which are Villani. In that case, now you can just run through the machinery, and what you will get is an estimate of the step length in terms of various constants, A, B, and C. I'm not going into the details of where the A, B, and the C come from. A and B essentially come from trying to make an argument to the proximity between the SDE and the SGD. And then I have to choose an initialization that you start the algorithm initialized from a density, which is L2 in 1 over mu s star measure. And rho initial has to be such that it is close to the Gibbs measure of S star by a certain amount, which exponentially depends on your time horizon parameter capital T. In that case, we can show that the expected loss of the neural net at T by S star minus the infimum is below epsilon. So it's kind of good to note that the epsilon occurs at 3 places here. One is determining the step length. One is determining proximity of the initialization to the Gibbs measure. And that determines that you're finally close to the global minimum of the loss. So T is a parameter which controls, in some sense, that gives you a trade-off between, if you increase the T, you relax the conditions on the initial distribution from which you have to sample the SGD starting point. So T kind of larger the T, more freedom you have in terms of where you sample the initial distribution from, sample the initial weights from. But if you use a larger T, you have to wait longer to get to the global minima. So it's a trade-off between where you initialize and how long you take to get to the global minima. So I think that's a very natural kind of a trade-off to end up with. That if you sample closer to the Gibbs measure, you will take sooner, you will get to the global minima. If you sample farther, you will take a long time. It's a pretty natural trade-off, I would think.
So just clarification. So what is lambda here?
Lambda is the, okay, like, go back. This is the regularized loss function. No, where am I going? Yeah. So I'm using this Frobenius norm regularized loss function. So this is the lambda. Yeah. It's not big, and I shall try to explain in it's not too big, and that's what we shall get to later on. And it's actually computable. Threshold is computable, and that's the key point here. That this is not an arbitrary constant; it's a computable constant.
So T is now iteration. So T.
Yes, T is a time horizon parameter, which parameterizes how far from the Gibbs measure you initialize. If you initialize farther, you take longer to reach. So the question was about what is lambda c. So it is computable. So we can actually prove that in the very standard case where we do a lot of the experiments, that if your data norm and the outer layer norm is normalized to have a product 1, and I'm considering sigmoid gates, then you can run through the calculation and compute the threshold is 0.125. It is a precise number. There's no ambiguity about what the threshold of regularization is. You have to use a 0.125 threshold for the theory to kick in. There is no claims being made about this being optimal or anything. Maybe there's a better analysis which can lower the threshold. Totally possible. It's a tighter inequality. There's a bunch of inequalities. It's like 7 pages of inequalities going around. If you can do a much tighter analysis of those inequalities, maybe you can lower the threshold further downwards. So the threshold value is not like, there's nothing fixed about it. It's improvable up to ingenuity of doing the inequalities right. But it's already not too bad. And it essentially comes from the Villani condition that asymptotically in weights, the gradients have to grow larger than the Laplacian. So this is the fourth Villani condition, which essentially determines the critical value of the regularizer. So it's worth pointing out where it comes from.
So where the uniqueness of solution comes?
The uniqueness of the global minima. Yeah. So we are not claiming it is unique because the convergence is in the loss term, loss value convergence. I'm not claiming anything about uniqueness of global minima here. It's a convergence of loss. Yes, question? Yeah. Yeah. Yes. So we are not making any arguments about uniqueness or minima. It's convergence of the loss value. That's why. It's all convergence of loss value, not convergence to a particular point. That's why the permutation is taken into account. Question.
When you talked about shear thought paper, you mentioned that they don't need Villani property for convergence of the SDE. They only need it for rate of convergence.
Yes.
Is that true in discrete time also, or is that only statement is true only in the SDE?
It is a statement about the FPS PD. So I don't know how will that filter into the discrete time analysis.
To go from the SDE to the discrete time, they do need Villani. They do need the rate.
They need Lipschitz smoothness. I don't think the Villani condition is needed to go to do the discrete transfer. The discrete transfer needs the smoothness of the loss function.
So you're primarily then using Villani property mainly to get the rate.
Yes, because I really want to do the rate thing, get all the rates. Okay.
Sorry, one more question. Is the if I don't care about the rate, is the convergence itself known in the literature?
Convergence of what?
Convergence of like essentially what you're doing, gradient descent, one layer, I mean 2-layer neural network.
So I can go back to that historical review that I had given. So if you remove the width assumption and the data assumption simultaneously,
okay.
I do not know of any proof of convergence of SGD on a neural network at this point. You have to make all results about SGD convergence on neural nets either need you to force the width to have asymptotic sizes, or if you work at a parametric width, you'll have to force something over the data structure. Either it's realizable or it's Gaussian, typically both, I think. So that's the trade-off. So how do you break both the assumptions simultaneously? That's the challenge. So here is one option in one class of nets. Thank you for the questions. A few more remarks. The gradient Lipschitz condition, as this has already come up in the questions, that the gradient Lipschitz condition is necessary to when we invoke the standard theorems to go from the SDE to the SGD. So which is why if you use a soft plus activation, which is like a smooth version of ReLU, I cannot get at this point a discrete time convergence, but I can get the SDE to still converge because that part of the story still works out fine. And that gives you a linear time convergence of the SDE to the global minima of the loss function. So this part we do not know how to convert into a discrete time at this point, because with the soft plus, I can't get gradient Lipschitz smoothness. Okay. So next thing to do is, how do we know that your value of the regularizer is not too bad? So this is a critical question that needs to be addressed in any such thing. One way to understand this is to say that if my regularizer were too high, I would have lost sensitivity of the dynamics to the data structure. So one way to do it is to do an ablation study. At the threshold values, let's inject more and more noise into the training data. If I inject more noise into the training data, I expect my SGD to underperform. So if I am still underperforming despite the presence of the regularizer, That's one way to argue that the regularizer is not overshadowing the main loss term. And that's what this shows, that as I increase the amount of noise in the training data, my test loss achieved is progressively getting worse, despite my regularizer being at the threshold. So this is like a evidence that the regularization is not washing out the effect of the main term. This kind of an ablation study is one way to establish that. Another way to think about the whole problem is, so where are we headed in terms of, where are we in terms of theory? So I like to show this plot for that. So what you see here is, we have sampled data from a particular function. I chose this function because this looks nice, basically. So it's an agnostic data setup. The x comes from a uniform distribution in d dimensions, is 20 dimensions. And the labels comes from some function, which I don't think is the exact neural, so I can claim it to be an agnostic data. Sorry, non-realizable data. And I'm adding some noise to it. And what you see in this plot is the y-axis is the best test loss attained by the neural network, where the x-axis is the value of the regularization. So I'm varying the regularization value here, at least for 5 orders of magnitude. And the various colors of the graph is for different widths of the net. So the smallest widths obviously has the highest test error. As I'm increasing the width, the test error starts to fall. And the training data is chosen in such a way that some of these widths are in the underparameterized regime, some of the widths are in the overparameterized regime. So the training data is chosen somewhere in the middle here. I think it was around 800, if I'm not wrong, in this experiment. So first 4 curves are in the underparameterized regime, then goes overparameterized. So whether you are in the underparameterized regime or in the overparameterized regime, the essential message of the plot remains the same, that there is only very little, barely 3.3 to 0.5, like that's all that is your essential loss in test error. For 6 orders of magnitude of variation of the regularization, my loss in test loss is 0.3 to 0.5. And that's a way to make an argument that you did not lose too much in terms of test loss, despite using a regularizer, which is slightly higher than what you might encounter in practice. And this kind of a picture is quite consistent across many widths, many data. You can repeat it. And we have done many iterations of this experiment up to our computational resource thresholds. And it's extremely expensive to do this experiment. I don't know of a way to do it faster. And no matter what you have tested, this picture pretty much remains the same, that there is barely 1 order of magnitude of loss of test error, despite 6 orders of change of the regularization value used. The red line is where the current theory threshold is, where my Villani function kicks in and the proof convergence starts. Everything to the left of the red line, which is the yellow part, is where, the best of my knowledge, there's no convergence proof. So this is like the theory space. Everything yellow is where I don't know how to write a proof. I don't know of anyone who has written a proof. And the blue space is where my proof kicks in. So can the red line be pushed to the left? I would believe so. There's no reason to believe that my calculations is optimal or tightest inequality that I've used. I have no such claims ever. So the idea for the next steps of the research is, now that we have broken the barrier in some sense, how much to the left can you keep pushing the red line? Currently, there's no theory in the yellow space. And just for sanity checking, we can repeat the experiment with realizable data also, where the output is coming from another neural net of the same architecture, but smaller number of gates. You can see the same pictures comes back. The regularization changes over 5 or 6 orders of magnitude, but the loss in the test accuracy is barely a factor of 2. So there is very little loss in test accuracy despite 6 orders of variation of the regularization. And again, the same picture, the yellow side is where theory is not known, blue side is where theory kicks in. Can we push the red line to the left? That's the next challenge. Okay, so let me start to summarize. Now that we know that here is a method of getting convergence of SGD, which I believe is a new way of getting convergence of SGD for neural networks, does it work elsewhere? Is my neural loss functions that I have studied the only ones which satisfies the Villani condition? I am optimistic, maybe not. Maybe there are more examples of neural nets with more interesting architectures, which are also probably Villani. And just that we haven't done that analysis yet. It was the first case that we could figure out. And not just architectures, the question also goes to the loss functions and the regularizers. There are squared loss is not the only loss function that is trained on. Frobenius norm is not the only regularization that is used in the real world. So there are all kinds of variations available out there in terms of architecture choices, loss function choices, and regulation choices. And it's a very natural question of whether the Villani idea will kick in again and again. I don't know. I'm optimistic. And the second question is characterizing the Poincare constant of the Gibbs measure of the loss function. Now that we know this is the length scale of SDD convergence, that's essentially what it tells you. That is essentially the length scale of convergence of time scale of convergence of SDD. How much is that? Like, can we characterize that? Can we compute it, bound it, something? What is the Poincare constant of the Gibbs measure of neural loss functions? This, I think, is a well-motivated question at this point, given the convergence results. And we would like to find that out. Then we can get much more interesting bounds on the runtime, etc., which are currently one of the most important implicit numbers in the convergence result is the Poincare constant, I would say. So computing that is, I think, a very interesting challenge, at least bounding it. And lastly, I would like to talk about, yes, question.
Why is the Poincare constant important? How does it show up?
It is in the, okay, if you go back to the thing, where did you go? This.
I know the clicker is very complicated.
Okay, this is very strange. So basically, if you go back to the theorem, the Poincare constant shows up here. It determines your time scale of convergence, essentially.
Okay, and this is Poincare constant of what?
Of the Poincare constant of the Gibbs measure of the loss function. So the stationary measure of the SDE. So that is the stationary measure of the SDE, and what is its Poincare constant? That is your time scale of convergence, essentially. That's one of the dominant factors. I would like to know how much is it. So this, I think.
Oh, so this Poincare constant controls how fast the SDE reaches the Gibbs measure?
Yes.
Okay, and so obviously it also constrains the rate of convergence.
Yes. So there's a lot of research has happened on understanding Poincare constants of various measures, but for neural Gibbs measure, this was not motivated earlier. That is an interesting question, even for neural networks. So now here is a very concrete motivation why we should think of the Poincare constant of neural Gibbs measures. Okay, and lastly, I would like to talk about this another interesting work where we have given Rademacher complexity bounds of what are called deep operator networks. So far, everything I've talked about was for standard neural networks. Standard neural networks are only so much fun. After some time, you want more fun. The more fun happens by taking two neural nets and taking a product of them. So if I take an inner product of the new outputs of two neural networks, then I get what are called deep operator networks. Deep operator networks are a fundamental deviation from standard deep learning theory because now your predictor is not a Lipschitz function at all. And this brings with it a whole lot of new complications. And the reason we want to do it is because it has been proven, there's an universal approximation theorem now that has been proven, that product of neural nets is an universal approximator for any operator between any two Banach spaces, which in turn means that you can solve any PDE by a neural network, by two neural networks. So every PDE we believe can probably be solved by set up a loss function over two neural networks. And these architectures are fundamentally new puzzles show up with it. There's a lot of exciting stuff that is going on currently. So I would say, and this is a regime where there is absolutely no training result. I am not aware of any training result at this point for product of neural networks, which is one of the most interesting directions, I think, for AI for science, if you think of it that way. If you want to solve PDEs, families of PDEs in one shot, you should train product of neural nets. And product of neural nets is where no training results are available. So here is an approach. Will this work? Will this idea of Villani functions still work in products? I think that's a very interesting question to think about. And this is the end of the talk. We still have time for questions. And please feel free to ask questions.
Let's thank the speaker.
Yes.
So, first of all, very nice work.
Thank you.
Compared to your first work, you know the complexity of optimizing of neural nets is exponential in terms of inputs. So,
Exponentially input dimension.
but for your second piece of work, now we got a linear rate of convergence.
Epsilon. Now when you bring exact optimization versus epsilon.
So I'm just curious, where this complexity here? I think they should have complexity match each other.
I don't know if there's a way to directly compare this. Exact optimization, there is an NP hardness result. When you want an epsilon accurate answers, there are hardness results for that also. You can come up with loss functions and neural net combinations on which you can prove that getting an epsilon accurate answer is a runtime lower bound. So in the approximation world, there are new lower bounds known. So it's not true that every loss that you can get arbitrarily fast runtimes for arbitrary width and arbitrary data. That is not possible. There are runtime lower bounds known for that. And typically those go through what are called SQ lower bounds. So there's a bunch of, not bunches, maybe 2 or 3 papers I'm aware of where people have been able to prove SQ lower bounds. So that does constrain runtime even in the approximation setting. So the NP hardness problem in some sense gets replaced, I would say, by this kind of runtime lower bounds.
So the situation is analogous to gradient descent versus ellipsoid method and convex optimization. Ellipsoid method has exponential dependence on dimension of gradient descent.
Yes, that's a good analogy.
Well, I'm just curious, right? So, where those complexity should be hidden somewhere in the code.
So in some sense, there is new complexity lower bounds here. I would put it that way.
Okay.
If you want.
The question is, you have this A and B that you did not present explicitly.
Yes.
Is there an exponential dependence in dimension hidden in those?
I don't think so. I do not think there's an exponential dimension hidden in them. As far as I know, there's no such dimensionality dependence hidden there.
Yeah, we can follow up that. Thanks.
So when you have this constraint that the initial distribution, W0 is initialized from a distribution that is not too far away from you.
So way to understand that is to say that, okay, I can use the board maybe. Yeah, I don't think anyone can see it, anyone online. So way to understand that is when you compute the error gets 2 terms. One that scales with the step length and one that scales with the distance to initialization. There are 2 parts to the error actually. One comes from the SD, SGD proximity argument. One comes purely from the FPS convergence. This is the FPS convergence runtime. So there are 2 parts to the error, FPS convergence and the SDE, SGD approximation guarantee. It's additive. How do you make the sum be below epsilon? Only one way I know how to break this interdependency, there are shared variables between them. Because S occurs here and S occurs here. There are shared variables. T occurs here and T also occurs here. So both the sources of error have shared variables. One way to break this dependency is to say, let me run it, choose a step length small enough that this goes to epsilon by 2. Let me initialize such that this independently goes to epsilon by 2. And then I can get the total error down to epsilon. One can equivalently state the result as this thing, but I think it's not intuitive to state the result as 2 terms. So I force it as initialization constraint. Question? Can you repeat the question?
When I train, the thing I want to know is, if I stop now, do I have the best possible loss, or should I keep training?
Don't ask a theorist. Some questions are not to be asked to a theorist. Keep training till you get a good result. Unless you know the Poincare constant, then come back.
If there are no other questions, let's thank the speaker again.